An Auto-Wye transformer configuration is a three-phase transformer connection that can convert a three-phase 208Y/120V system to a three-phase 230V system. To determine the required transformer rating for an Auto-Wye connection feeding a 400 amps panel board, consider the following. Firstly, the panel board amperage is 400 amps. Secondly, the panel board voltage is 230 volts, line to line. Thirdly, the load factor is assumed to be 75% or 0.75. The kVA calculation is as follows: kVA equals panel board amperage multiplied by line-to-line voltage multiplied by the load factor. Thus, kVA equals 400 amps multiplied by 230 volts multiplied by 0.75, which equals 74,250 volt amps. Therefore, the required transformer rating for the Auto-Wye connection is 75 kVA. The conductor sizing on the engineer's diagram may not seem correct because the Auto-Wye connection has a higher current carrying capacity than a conventional Delta-Wye connection. The higher current carrying capacity is due to the fact that the Auto-Wye connection has a zigzag pattern, which increases the magnetic coupling between the windings. Advantages of the Auto-Wye connection include firstly, a higher current carrying capacity compared to a Delta-Wye connection. Secondly, it can provide a higher voltage level. Thirdly, it requires less copper than a Delta-Wye connection. The transformer should be rated for continuous operation. The transformer should be protected by a circuit breaker or fuse that is rated for the transformer's full load current. The conductor sizes should be verified by a qualified electrician to ensure they meet the requirements of the National Electrical Code. When determining the appropriate conductor size for an Auto-Wye transformer connection, several factors must be considered to ensure compliance with the National Electrical Code and safe operation. Firstly, determine the transformer's primary and secondary currents. Use the kVA rating and voltage levels to calculate the current on both sides of the transformer. The formulas are: primary current equals kVA times 1000 divided by the square root of 3 multiplied by the primary voltage. Secondary current equals kVA times 1000 divided by the square root of 3 multiplied by the secondary voltage. Secondly, select the appropriate conductor size. Refer to NEC Table 310.15b16, formerly Table 310.16, to determine the ampacity of conductors based on their insulation type and temperature rating. Choose a conductor size with an ampacity equal to or greater than 125% of the transformer's primary and secondary currents, as required by NEC Section 450.3b. This accounts for continuous loading. Thirdly, consider voltage drop. Calculate the voltage drop on both the primary and secondary sides of the transformer to ensure it remains within acceptable limits. The NEC recommends a maximum voltage drop of 3% for feeders and 5% for the total feeder and branch circuit. Use appropriate voltage drop calculation formulas and adjust conductor sizes accordingly to minimize voltage drop. Fourthly, account for ambient temperature and conductor bundling. Apply correction factors to the conductor ampacity based on the ambient temperature and the number of current carrying conductors bundled together, as specified in NEC Table 310.15b2 and 310.15b3. This ensures the conductors can safely carry the load current under the given conditions. Fifthly, choose the correct insulation type. Select conductor insulation suitable for the operating temperature and environmental conditions. Common insulation types include THHN, THWN, and XHHW. Refer to NEC Table 310.104 for allowable conductor insulation types and their temperature ratings. Sixthly, ensure proper overcurrent protection. Install appropriately sized overcurrent protection devices, such as circuit breakers or fuses, on both the primary and secondary sides of the transformer, as required by NEC Section 450.3. The overcurrent protection should be sized no greater than 125% of the transformer's rated primary and secondary current. Seventhly, verify compliance with local codes and regulations. Check with local authorities and building departments to ensure compliance with any additional local codes and regulations related to transformer installations and conductor sizing. Eighthly, use appropriate terminals and connectors. Select terminals and connectors that are rated for the conductor size and material being used. Ensure proper termination and torque connections to prevent overheating and loose connections. Ninthly, label conductors clearly. Label all conductors at termination points to indicate their purpose and circuit identification. This helps with future troubleshooting and maintenance. Tenthly, consult a qualified electrician. It is highly recommended to consult a qualified electrician or electrical engineer to perform the conductor sizing calculations and ensure compliance with all applicable codes and regulations. They can provide valuable expertise and guidance to ensure a safe and reliable installation. The zigzag pattern in an Auto-Wye transformer contributes to its higher current carrying capacity compared to a Delta-Wye transformer through several mechanisms. Firstly, improved magnetic coupling. The zigzag connection increases the magnetic coupling between the windings of the transformer. In a conventional Delta-Wye transformer, the magnetic flux paths are more distinct and separate for each phase. In contrast, the zigzag connection interweaves the windings of different phases, allowing for greater interaction and cancellation of magnetic fluxes. This improved magnetic coupling results in a more efficient transfer of energy between the primary and secondary windings. Secondly, reduced impedance. The zigzag connection reduces the impedance of the transformer, particularly the zero-sequence impedance. Zero-sequence impedance is the impedance offered by the transformer to zero-sequence currents, which are currents that flow in the neutral conductor and are caused by unbalanced loads or faults. By reducing the zero-sequence impedance, the zigzag connection allows for high fault currents to flow during ground faults, which improves the sensitivity and speed of ground fault protection devices. Thirdly, harmonic current mitigation. The zigzag connection helps to mitigate harmonic currents in the system. Harmonic currents are non-sinusoidal currents that are generated by nonlinear loads such as electronic devices and adjustable speed drives. These harmonic currents can cause voltage distortion, overheating of equipment, and interference with sensitive electronic devices. The zigzag connection provides a path for harmonic currents to circulate within the transformer, reducing their impact in the rest of the system. Fourthly, increase fault current capacity. The zigzag connection increases the fault current capacity of the transformer. Fault current is the current that flows during a short circuit or other fault condition. The zigzag connection allows for higher fault currents to flow without damaging the transformer, which improves the reliability and safety of the system. Fifthly, balance voltage support. The zigzag connection helps to balance voltage levels in the system. A balanced voltage can occur when the loads on different phases are not equal. The zigzag connection provides a path for current to flow between the phases, which helps to equalize the voltage levels and prevent voltage imbalances. Sixthly, enhance voltage regulation. The zigzag connection improves the voltage regulation of the transformer. Voltage regulation is the ability of the transformer to maintain a constant output voltage under varying load conditions. The zigzag connection reduces the voltage drop across the transformer, which improves the voltage regulation and ensures that the load receives a stable voltage supply. The advantages of using an Auto-Wye transformer connection compared to a Delta-Wye connection can be further elaborated as follows. Firstly, higher current carrying capacity. As previously mentioned, the Auto-Wye connection has a higher current carrying capacity compared to a Delta-Wye connection. This is due to the zigzag pattern of the windings, which increases the magnetic coupling between the windings and reduces the impedance of the transformer. This higher current carrying capacity allows the Auto-Wye transformer to supply more power to the load without overheating or experiencing voltage drop issues. Secondly, improved voltage regulation. The Auto-Wye connection provides better voltage regulation compared to a Delta-Wye connection. Voltage regulation is the ability of the transformer to maintain a stable output voltage under varying load conditions. The Auto-Wye connection reduces the voltage drop across the transformer, which improves the voltage regulation and ensures that the load receives a stable voltage supply. Thirdly, reduced zero-sequence impedance. The Auto-Wye connection has a low zero-sequence impedance compared to a delta-Y connection. Zero-sequence impedance is the impedance offered by the transformer to zero-sequence currents, which are currents that flow in the neutral conductor and are caused by unbalanced loads or faults. The low zero-sequence impedance of the Auto-Wye connection allows for higher fault currents to flow during ground faults, which improves the sensitivity and speed of ground fault protection devices. Fourthly, harmonic current mitigation. The Auto-Wye connection helps to mitigate harmonic currents in the system. Harmonic currents are non-sinusoidal currents that are generated by nonlinear loads, such as electronic devices and adjustable speed drives. These harmonic currents can cause voltage distortion, overheating of equipment, and interference with sensitive electronic devices. The Auto-Wye connection provides a path for harmonic currents to circulate within the transformer, reducing their impact on the rest of the system. Fifthly, reduced copper usage. The Auto-Wye connection requires less copper than a delta-Y connection for the same kVA rating. This is because the Auto-Wye connection utilizes a portion of the winding for both the primary and secondary sides, which reduces the overall amount of copper needed. Sixthly, cost savings. The reduced copper usage of the Auto-Wye connection translates to cost savings in terms of materials and manufacturing. The Auto-Wye transformer is generally less expensive to manufacture compared to a delta-Y transformer of the same kVA rating. Seventhly, smaller size and weight. The Auto-Wye transformer is generally smaller and lighter than a delta-Y transformer of the same kVA rating. This is due to the reduced copper usage and the more compact design of the Auto-Wye connection. Eighthly, improved efficiency. The Auto-Wye connection can offer improved efficiency compared to a delta-Y connection, especially under light load conditions. This is because the reduced copper losses and improved magnetic coupling of the Auto-Wye connection result in lower overall losses. The National Electrical Code provides guidelines for sizing conductors and overcurrent protection for transformers, including Auto-Wye transformers, to ensure safe and reliable operation. Firstly, conductor sizing. NEC Section 450.3b covers the overcurrent protection of transformers rated over 600 volts, nominal, and NEC Section 450.3 covers the overcurrent protection of transformers rated 600 volts, nominal or less. These sections dictate that the primary and secondary conductors must be protected by overcurrent devices sized according to specific rules. Generally, the primary conductors must have an ampacity of at least 125% of the transformer's rated primary current, taking into account any applicable correction factors for ambient temperature and conductor bundling. The secondary conductors must also have an ampacity of at least 125% of the transformer's rated secondary current. However, there are exceptions to this rule depending on the transformer's impedance and the available fault current. Secondly, overcurrent protection. NEC Section 450.3 provides detailed requirements for overcurrent protection of transformers, including the sizing of circuit breakers or fuses. The primary overcurrent protection device should be sized no greater than 125% of the transformer's rated primary current, unless the transformer's impedance is 6% or less, in which case the overcurrent device can be sized up to 300% of the rated primary current. The secondary overcurrent protection device should be sized no greater than 125% of the transformer's rated secondary current, unless specific conditions are met that allow for higher settings. Thirdly, tap conductors. If the transformer has tap conductors, which are conductors that are tapped from the primary or secondary windings, the NEC provides specific rules for sizing and protecting these conductors. NEC Section 240.21b outlines the requirements for tap conductors over 10 feet long, and NEC Section 240.21c covers tap conductors not over 10 feet long. These sections specify the minimum ampacity of the tap conductors and the maximum size of the overcurrent protection devices. Fourthly, coordination. The NEC emphasizes the importance of coordinating the overcurrent protection devices on the primary and secondary sides of the transformer to ensure proper selectivity and prevent nuisance tripping. Coordination studies should be performed to determine the appropriate time current characteristics of the overcurrent devices and ensure that they will operate in the correct sequence during fault conditions. Fifthly, grounding. The NEC also provides requirements for grounding transformers to ensure the safety of personnel and equipment. NEC Section 250.30 covers the grounding requirements for separately derived systems, which include transformers. This section specifies the methods for grounding the transformer's neutral point and connecting the grounding electrode conductor. Sixthly, labeling. The NEC requires that transformers be labeled with specific information, including the kVA rating, primary and secondary voltages, and impedance. This information is essential for determining the correct conductor sizes and overcurrent protection settings. Seventhly, documentation. It is important to maintain accurate documentation of the transformer installation, including the conductor sizes, overcurrent protection settings, and grounding connections. This documentation should be readily available for future reference and maintenance. Eighthly, qualified personnel. The NEC emphasizes the importance of using qualified personnel to install and maintain electrical equipment, including transformers. Only qualified electricians and electrical engineers should perform these tasks to ensure compliance with the code and safe operation. It is crucial to consult the latest edition of the NEC and seek guidance from qualified professionals to ensure compliance with all applicable codes and regulations when sizing conductors and overcurrent protection for transformers. Proper conductor sizing and overcurrent protection are essential for the safe and reliable operation of transformers. Always adhere to NEC guidelines and local regulations and consult with qualified professionals for any specific questions or concerns.